All right, ready to go? This is part 2 of the analysis of variance chapter. Well, chapter section, the analysis of variance lecture. So let's dive in. In this chapter, we're going to actually have some details and learn how some of this stuff works. So let's review quickly. Analysis of variance, its trick, the way that we can compare multiple groups at once with only a single test. Although we don't find out all the different differences among them, all we find out is that sometimes we think there is at least one pair that is different, maybe one, maybe more, or we think there isn't. Anyway, the way we do this is that we compare between and within group variances. So we look at the variance, the variability, usually specified as the quantity we call variance, within each of the groups. We average that together. And then we look at the variability among the group means themselves, and we compare those two together. The way we do it is that we calculate the between groups variance using some formulas. I'm not going to go into those formulas in this class. I don't expect you to know them. If you want to figure them out, there's a million resources, and I might put up a lecture that goes through the details if you're really interested. But for this course right now, I'm not requiring it, but I do want you to understand the way things work and why things happen the way they do, how to interpret the outcome. So the between group variance is treating each mean as a data point, each group mean, and based on the deviations from each observation, from its group mean, squaring those, getting a variance for each group, averaging those variances together. I'm sorry, I just messed that up. So looking at each, the variance of each group mean from the grand total mean, which is the mean of the individual means. That gives you the variance between the groups. The average within groups variance is what I was saying a minute ago, the variance of the regular observations in each group. So each group's observations, looking at the squared deviations from the mean of that particular group. We average all those things together. We compare between to within by dividing. We make a ratio out of them. That's a very effective way to compare any two numbers. Always between divided by within. And if this ratio is bigger than we would expect under the null hypothesis, then we reject that null hypothesis. Now, the null hypothesis is usually there are no differences among the groups, and we don't usually write that in symbols. It's more common to write it just in words. Sometimes people say h0 colon mu1 equals mu2 equals mu3, however sample means you have. So you're saying the means that these samples came from in the population are all equal. But then the alternative hypothesis, you can't just say they're not all equal. You can't say one is equal. There's all these possibilities for which ones might be equal and not equal. So we usually just write out a phrase, something like, not all the means are equal, or at least two means differ from each other, or something like that. So writing the hypothesis out in symbols isn't as easy. So sometimes we just say null hypothesis, all means are equal in the population. Alternative hypothesis, in the population, at least two means are different from each other. Something like that. So everything comes down to this: the between groups variance divided by the within groups variance. Now we have different names for these. It's going to be sum of squares between divided by degrees of freedom between, and then within is sum of squares within divided by degrees of freedom within. But this is it: the variance between means divided by the average variance within groups. That makes one number. Right? When you take something and divide it by something else, now it's one number. And that number, we're looking to see if it's really big. If it's big, then that means there's a lot more between groups variance than we would expect if there was nothing going on. Now, when I say if there is nothing going on, I'm saying if the null hypothesis were true. If those things are about the same as each other, then there's probably nothing going on. That's what we would expect if nothing was going on. So, of course, there's a sampling distribution to describe this. If the null hypothesis is true, we wonder what is the true ratio of the variance between groups, between group means, to the variance within groups, the average variance within groups. And in general, if the null hypothesis is true, it'd be about 1. In other words, the variance between the group means will be about the same as your average variance between any other 2 points, or 3 points, or 4 points. So the variance between the means will be behaving as if they were just regular old normal observations. And so the ratio will be about 1. So if you get that ratio about 1, you know that you didn't find anything. There's nothing going on. Those means differ by a very uninteresting amount. So if the null hypothesis is true, then we would expect that on average that ratio would be 1. If we were to randomly sample from the population and keep doing studies and getting groups and calculating the within and the between group variance over and over and over again, of course, the ratio wouldn't be 1 all the time. Sometimes it would be bigger, sometimes it would even be smaller. So the sampling distribution is the answer to what are all the possibilities of that ratio if the null hypothesis is true. If there isn't really any difference between the groups in the population, then the ratio of between to within on average is 1, but with random sampling could be a lot of different values. It could be an infinite number of values, actually. So we look at all those possibilities, and then we take our particular between groups variance divided by within groups variance, our particular number, and we put it in that distribution and see where it fits in. So the mechanics of it look like this. We calculate the sum of the squared deviations of the group means from the total mean, which is sum of squared between, and we divide it by its degrees of freedom, and that gives us a variance. And the sum of squared deviations of each observation from their group mean, which is the sum of squares within, and we divide it by the degrees of freedom within, so that gives us our estimate of within groups variance in just individual observational variance. And that's where we get our between groups variance, and we call that mean square, the mean square. This is just terminology that goes back 100 or more years to R.A. Fisher, who invented this process at the beginning of the 20th century. So the mean square between is our estimate of the variance between the groups, or the variance among the group means. And then the mean square within is what we call the variance within the groups. When we divide those by each other, and we come up with a single number, we call that number F, in honor of R.A. Fisher, although many students for years have had different little nicknames for why it's called F. Actually, probably all the same nickname. Now, we sometimes put observed because there are theoretical F values, but here is our observed F value. There's also a critical F value, but here's our observed F value. Just like with T, you have T observed and T critical. We have F observed and F critical. So our observed F value, we look in the distribution of F scores. Now, these F values, there's a different distribution for every different combination of degrees of freedom. So with the T, there's an infinite number of distributions, right? There's a distribution for 1 degree of freedom and 2 degrees of freedom and 3 degrees of, up to an infinite number of degrees of freedom. Same with F, except you have to consider 2 degrees of freedom. When you find your F value, you have to look up in the table, usually a table that has like the columns tell you about the degrees of freedom between, and the rows tell you about the degrees of freedom within, and you have to find their intersection. That's because there's a different distribution for every combination of between and within degrees of freedom. You don't have to really worry about that. You just look something up in a table, or you use a computer at the end. But the F observed, you look, when you get the correct F value, you just plunk your F observed value right on there. And any value beyond that, it's always to the right. There's no two-tailed anymore. Any value beyond that, all of those together, the area under that curve, and of course we say the area under the curve is 1 in general, the percentage of the area under that curve is P. And we want P to be less than 0.05 or 0.01, whatever our alpha is set at for this study. So that's how we do this. Now, sometimes we look up an F critical and we find out where the F critical that cuts off like 5% or 1% for alpha. And then we compare F observed to F critical. And it's a simple comparison because F observed just needs to always be bigger to reject the null hypothesis. It's right skewed, and so it's always, is F observed bigger? So we're looking at the p-value. P is less than 0.05 or P is less than 0.01. So the Anova table is a traditional way that we represent the results of an analysis of variance. It includes all sorts of information that later researchers can use to reanalyze your data in various fun ways. And it tells you a lot about what happened in the study. It gives you some good information. So we have a source column, and the source just says between and within. In other words, the source of variance. So each observation, the way this table is setting things up, each observation, its particular value is due to 2 influences. One influence is the influence of its own group, and that's within groups variance. And another influence is the influence of, oh, sorry, one influence is its own group, and that's between groups variance, actually. And then the other influence is just random sampling, and that's within groups variance. So between groups variance is the effect of whatever your independent variable is, and within groups variance is just random sampling variance. It's just random variance. So we put numbers in there. There's formulas to calculate these things. Sometimes we calculate a total as well. It's not important to the analysis, but it's in the olden days with hand calculations, it was important to check your total. We have to know the degrees of freedom for each one of these quantities, for the sum of squares between and the sum of squares within. And then you divide the sum of squares by its degrees of freedom to get its mean square. Then you divide the mean square between by the mean square within, and you get the F value. And then you look them in a table, or you use your computer, or your computer does this all for you, and tells you either a specific p-value, like we have here, or it'll just tell you whether p is less than 0.01 or 0.05 or 0.001, whatever your alpha value is. So sometimes you find a specific p-value, like if you're using a computer, but if not, then you just find a yes or no decision. Is it less than my alpha value? You decide alpha is, say, 0.05, and you decide whether p is less than that. In this case, it's not. 0.18 is much bigger than 0.05. So the sum of squares is the heart of ANOVA, and the sum of squares is just variance. The sum of squares is the numerator of variance, specifically. So here's the variance formula. This isn't sum of squares, this is variance. The numerator is this, the sum of the squared deviations of each observation from its mean. The sum of the squared deviation of each observation from the mean of all the observations. That's why we use the shorthand version, sum of squares, because it means sum of the squared deviations of the observations from their mean. And we have various kinds of sum of squares. And when we divide the sum of squares by degrees of freedom, then that makes the sum of squares into mean square, which is variance. The within groups or the between groups variance. Now, in the regular variance formula, the degrees of freedom is indicated by n. But of course, when you do actual analysis of variance, it's not just n, it's something a little bit different. As you recall, this should actually be n minus 1, right? I used the simplified version, but it should be n minus 1, which is degrees of freedom for like a t-test or a confidence interval for t. In general, the degrees of freedom for a particular part of the analysis of variance, or any analysis, is the number of observations being considered minus the number of population parameters that are being estimated in that part. You don't have to necessarily know this. You should figure out, k minus 1 and n minus k. That's about all. But I'm just explaining where this comes from, not that you have to understand this at a deep level. So the degrees of freedom between are always k, which is the number of groups in your analysis. So if it's a 3-group comparison, k will be 3, minus 1. So if there are 3 groups, k minus 1 is 2. So the degrees of freedom between would be 2. So the number of groups is the n being considered, because the degrees of freedom between goes with the variance between, in which you consider the group means to be individual observations. So the number of groups, or the number of group means, is n. And we call it k in this case. But it's the number of things that you're dealing with. And you subtract 1, because to calculate the variance of anything, you have to calculate a mean to have a deviations. And since this is a procedure where everything we do is estimating something in the population, when we calculate the mean in order to calculate our variance, then we have estimated a population parameter, and we've reduced our uncertainty by doing that. So to prevent double dipping and doubling up on that, or doubling up on uncertainty when we should just recognize the uncertainty, I guess that's one way of saying it, then we subtract 1. So the number of groups is k, and we had to estimate one mean to calculate the variance between groups, and so we subtract 1. The one mean we calculated was the grand mean. The degrees of freedom within is calculated as the n of your total study, everybody in your study, minus k. So you can think of it as n1 plus n2 plus n3, like the individual groups. That's n. That's all the observations you have. But then you subtract k, because you estimated one population mean. You estimated a group mean in the population every time you calculated a sample mean to calculate the variance of an individual group. Every time you calculated a sample mean, and you had to do that once per group to get your variance, then you were estimating a population mean, so n minus k. If you didn't get all this, just try and remember k minus 1, n minus k. and how to apply them. So let's go back to your Anova table. You've got your basic sum of squares here. And once you've got your degrees of freedom, sum of squares divided by degrees of freedom gives you the mean square. You do that for between, and you do that for within. Now the F ratio is the mean square between divided by mean square within. In other words, our estimate of the variance between means divided by our estimate of the overall variance, the average variance within groups. The F distribution is that distribution you saw a few minutes ago that is the sampling distribution of the ratio of any two variances. Our particular ratio of variances is called F observed, and we have to know the degrees of freedom that went into creating that. So the degrees of freedom for the between and the degrees of freedom for the within to look up the correct distribution to compare in. And we just want to know, is our ratio bigger than we would expect if the null hypothesis were true, which would mean that the only differences between our group means came from random sampling fluctuations. F ratios are always asymmetrical, therefore they're always one-tailed, which is a nice thing. You never have to worry about one versus two-tailed with an analysis of variance. Hypothesis testing here is the same as hypothesis testing with everything else. You state your null and your alternative hypotheses. You draw a diagram and you label alpha. You look up your F critical value and you state your rejection rule, although I'm not going to have you do this. I'm going to have you interpret the results of hypothesis tests with Anova, but not do them yourself. Calculate F observed, which you don't have to do. State your decision about the null hypothesis, and then state your conclusion in terms of the variables, etc. So here's an example with data you've already seen, but kind of remixed slightly with how we're interpreting it. Let's say you're studying the number of children by political party of the parents. Do people with different political preferences differ in the number of children they have? And let's say alpha is 0.01 this time. Let's say we randomly sample some families, very few families, so it's easy to follow the math. Self-identifying as Democrat, Republican, or Tea Party. So find the sum of squares between. So let's look at the data here. The number of children by political party. You can see there's 3 families in the Democrat category, 3 in the Republican, and 3 in the Tea Party category. 1 child, 0 children, and 2 children, 5 children, 2 children, 4 children, 5 children, 1 children, 3 children. And you can look at the mean. The mean of the Democrats here is 1 child, Republicans is 3.6 children, and Tea Party 3.7. Tea Party 3.0 children. The grand mean is 2.5, 2.6. So here we have the data. We have the mean of 1 here for Republicans. The average number of children is 3.7. Tea Party is 3.0. The grand mean, the average number of children in the entire group of 9 families, is 2.6. We've got, averaging up the sum of all these kinds of things, which you need to do for certain calculations. You can ignore that right now. We apply a magical formula to find the sum of squares between, and we find that it's 11.56. So the sum of the squared deviations of the means, 1.0, 3.7, and 3.0 from their grand mean, which is 2.6, is 11.56. So finding the sum of squared within, then we look at the variance, part of the variance within each group. We apply a magical formula to that, and we find that the sum of squares within is 14.67. You add those up and give the total sometimes, even though that's not important. It's just to check and make sure you're doing your math right. So let's do a graph of this, a little number line graph. There are the Democrat children, 0, 1, and 2. There's the mean of the Democrat children. There are the Republican families, 2, 4, and 5. There's their mean. And the Tea Party families, 1, 3, and 5. And there's their mean, which is 3. So the grand mean is right here. And the deviations of the individual means from the grand mean are represented right there. So that's basically the sum of squares, or the variance between groups. Sum of squares between, 11.56. So finding the mean squares within, the way we did it was the same data, but for the Democrats you find the deviations. So the deviation of 1 from itself is 0, but the deviation of 0 from 1 and 2 from 1, you square those, you get 2. The Republican sum of squared deviations, they're represented right there. That's how far each of the Republican observations is from its mean. And the sum of squares ends up to be 4.67. The Tea Party has its own deviations going on here. And of course, one of the observations is the mean, so the deviation is 0. So the sum of squares for the Tea Party is 8. You add those things together and you get 14.67. So that's the sum of squares within. The F ratio is mean square between divided by mean square within. Your p-value, your textbook, as I said, doesn't have a p-value. I found one on the line at Stanford here, and I found that the F critical for alpha equals 0.01 for 2 and 6 degrees of freedom is much bigger than 5, whatever that was. Now it's 10.9, so definitely not rejecting the null hypothesis here. P is greater than 0.01, so we would say the evidence does not support the hypothesis that the number of children per couple differs by political party, and then in parentheses we put our statistics. F, so that's the observed F of 2 and 6 degrees of freedom is 2.36, P is greater than, and then you put your alpha value that you used to test things in your study. So what do you need to know for this class? You don't need to know how to do those calculations, but you should understand what sum of squares between is and sum of squares within is, what mean square between, mean square within, what degrees of freedom between and degrees of freedom within is. If somebody gave you those numbers and calculated them for you, you should be able to put them into an Anova table and figure out everything up to F. And then I suppose if you felt like finding a table online, you could figure out the critical F, etc. But you should be able to plug those in and figure out the F ratio. You should understand the logic behind why we compare between and within groups variability and how that actually tells us about differences between means, how that judo happens. We use variability, but we end up knowing about means. Kind of cool. So can you answer conceptual questions about that? Conceptual questions about, why we do that? What does it tell us? If there is large variability here and low variability here, what does that mean about the differences between means, etc.? Can you convert diagrams of distributions, like those curves that I had at the beginning of this lecture, into mean square between and mean square within terms? Can you talk about those in those terms and say, oh, these distributions are really spread out and no overlap, therefore big mean square between, small mean square within will probably reject the null hypothesis? Can you do that? Can you set up an Anova problem, like saying, okay, you've got 4 groups and this and this and this, and then have a hypothesis like, is there a significant difference between these 2 of the groups, or something along those lines? Can you interpret SPAS results both from handwritten mathematics and from Anova? And then if you use R, interpret the results from R as well. Can you interpret what the computer spits out at you or what a calculating person spits out at you? I hope they don't really spit. That would be gross. And then can you interpret output from computers? So I already said that, so now I'm repeating myself. So this is what you need to know for Anova for this class. You don't need to calculate analysis of variance. Maybe in some future semester I'll teach the students to do that. If you want to learn how to do that, I'll definitely work with you on office hours and show you how to do it. It's not terribly difficult. It's kind of a pain, takes a little while, but it's not difficult and it really shows you what's going on. But I'm not going to require it of the people in this class. Now I'm going to kill this here. I'm going to stop the screen sharing, go back to regular. Here I am in my office. Oh, look how happy I am. Office time. The happiest time ever, and I'm done.